We're going to continue with Chapter 13, and we're going to specifically talk about experiments today, specifically randomized comparative experiments. In an experiment, the experimenter must identify at least one explanatory variable, which is called a factor, to manipulate, and at least one response variable to measure. An experiment will manipulate factor levels to create treatments. They will randomly assign subjects to these treatment levels, and they will compare the responses of the subject groups across treatment levels and groups. In an experiment, the responses that we obtain from people, animals, things, etc. are called experimental units or subjects/participants. Typically, if it's a person or an animal, they're called a subject or a participant, and objects are then called experimental units. Typically, if you want somebody to be a part of a study, you don't call that person an experimental unit. You're more likely to volunteer to be a participant, not a unit. The specific values that the experimenter chooses for a factor are called levels of the factor. For example, if you're testing a migraine medicine, but you're not sure what the proper dose is going to be, you might give a half dose and then what you think a full dose is. Those are two different levels of the factor of the medication. A treatment is the combination of specific levels from all the factors that an experimental unit receives. So sometimes an experiment will have more than one factor. Maybe they're testing the medication as well as how lighting affects it. Then we have two factors, and so a combination of the different levels, low light or natural light or fluorescent light, how those affect the headache as well, paired with the medication. So a treatment group is going to be the combination of the different levels for the different factors. There are 4 principles for experimental design. So 4 things that need to be included in an experimental design. The first one is control. We want to control the environment of the experiment by making the conditions as similar as possible for all treatment groups. Again, taking the headache medication example, maybe you're only testing the medication. So in that case, the people that are taking the medication, you might want to make sure that they have like the same level of headache, or maybe they're in like a similar environment. So because light does have an effect on a headache, maybe you want to make sure that they're all in the same type of lighting. Control what you can. Obviously, you won't be able to control everything, but we try to do what we can at least. When we do this, we're controlling extraneous sources of variation, and therefore we reduce the variability of responses. This makes it easier to detect differences among treatment groups, so we're able to actually determine if something really is statistically significant or not, and it also works to prevent from affecting the response variable. This is slightly different than a control group. The control group is the group that receives the control treatment. Oftentimes, this is a group that receives no treatment at all. So again, in our headache medication example, you might have one group that receives a full dose, one group that receives a half dose, and one group that receives no medication at all. That group is called the control group. And the reason for a control group is so that way when you're looking at the response variables from the different treatments, you can kind of compare the medication to people who didn't receive it. So did the medication actually work faster for the headache to go away than those people who didn't receive medication at all? Let's look at another example. Suppose we heard that drinking a specific sports drink before running causes you to run faster. You want to test this by drinking it and then go running. But you need to compare the time with the drink to the time of running without the drink. The treatment of not drinking the sports drink is called the control. This is different from the previous slide from controlling the situation. And again, when you are controlling the situation, you obviously can't control everything. You just want to do the best that you can. The next principle of the experimental design is to randomize. What this means is that you randomly assign subjects to the different treatment group. Now, I want to be specific here. In a survey, what you are doing is you are taking a random selection of subjects. You're identifying your population and you're randomly selecting them. An experiment doesn't have to have randomization in this way. For example, if you are testing a new cancer treatment, you are not testing it on people who don't have that type of cancer. So you're not going to randomly select from the population. you will take people with that specific illness. And then the people that you have as part of your study, you will then randomly assign those people to the different treatment groups. What this does is allows us to equalize the effects of uncontrollable or unknown sources of variation. Obviously, we try and control what we can, but randomization kind of takes care of the stuff that we can't actually control. This does not eliminate the effects of these sources, but it does spread them out equally among the different treatment groups, so we can kind of see past them. And it protects us from effects that we don't even know about. So underlying variables, which are called confounding variables, and we'll talk about in the next video. It also randomizes the differences among the different treatment groups to cancel out bias. So each group might be biased, but as long as it was a random assignment of the subjects, then each group will end up being biased in the same way, so the bias won't actually affect our results. And speaking of bias, that kind of leads us to blinding. So in an experiment, having a source of bias within each treatment group is not the end of the world, because as long as we used randomization, it will work. However, people can tend to be biased, which is where blinding comes in. We as humans are susceptible to errors in judgment. When we know what treatment was assigned, it's difficult not to let that knowledge influence our assessment of the response. In order to avoid this, we use blinding. There are two main classes of individuals who can affect the outcome of the experiment. Those who could influence the results. So the subjects, the people who are administering the treatments, the technicians, and then there's those who are evaluating the results. There are judges, treating physicians, somebody who is just evaluating what that response variable is. A single blind experiment is when one of those two groups are blinded. Either the people don't know what treatment they are receiving, or those who are evaluating don't know what the treatment was for the group that they're looking at. Double blind is when both classes are blinded. Typically, double blind is the best way to go. That being said, sometimes it is impossible to double blind, and you can only have a single blind experiment. And that's okay if that's how it falls. But we try to double blind when we can. One way to double blind, or to blind the subjects of what treatment they're getting, is with a placebo. A placebo is a fake treatment that looks like the treatment's being tested, and it's the best way to blind subjects from knowing whether or not they're receiving the treatment. For example, with our headache medication, the people who are getting the full dose and the half dose will physically be taking a pill. The people who are not getting any medication, instead of just not having them take something, we will give them a pill that is not the medication, and they take that instead. So that way they are still taking something, but they don't know if they have the placebo, the full dose, or the half dose. What happens a lot of the times in this situation, though, is that we get something called the placebo effect. So sometimes it's all mental. The act of actually having a treatment done to you, whether it's a treatment that works or not, makes you think that you're going to improve. When the placebo effect is when subjects being treated with a placebo actually improve. So those people who got the sugar pill and the headache medication, all of a sudden their headache magically goes away. That's not really how it works. But this does show the importance of effective blinding and using comparative treatments with a control. The third of the 4 principles for experimental design is to replicate. This means that we need to have multiple subjects in each treatment group. So we need to use enough subjects in each treatment group so that any differences between the treatments can be distinguished from chance differences in the group. Only by replication can you see the variability of responses. Again, I'm going to go back to the headache medication. If each group only has one person, and one person that took the placebo assumed they had the full dose, and they're claiming that their headache went away right away, well, now we don't think that the medication actually worked because the person who didn't have it had the same response time as the person who actually got the medication. If we have 10 people in each group, yes, maybe the placebo effect worked on one person, but the other people didn't report any change in their headache, so then we can average it, and then we can find the average response time for the headache to go away. And in that case, we can take the averages and see that the medication did actually work, or maybe it actually did not work, but we can see it better if we have multiple people within each group as compared to just having one person. When you are doing an experiment, it is often helpful to diagram it. This is not a requirement, although I probably on your test will ask you to diagram the experiment, but it is really helpful. So down below, I have a diagram which emphasizes the random allocation of subjects to treatment groups. The separate treatments are applied to these groups and the ultimate comparison of the results. So we have our random allocation, which, by the way, when you are designing an experiment, it is not enough to just say that you are going to randomly assign subjects to the treatment groups. You actually have to describe how that random assignment would go. So you need to explain that you would use random numbers, whether or not you can have repeats, and all of that good stuff. Then you would put them into the two groups, explain which group received which treatment, and then we compare our results. So let's go ahead and look at an example of designing an experiment. A completely randomized experiment in one factor is the simplest kind of experiment, and that's where we're going to start. So for example, an ad for Optigrow plant fertilizer claims that with their product you will grow juicier, tastier tomatoes. We're going to test this claim. We will need to grow tomatoes both with and without the fertilizer, but we're going to need a better plan than just that. The first thing we need to do is we need to plan. We need to state what we want to know. In this case, we want to know if tomato plants grown with Optigrow will produce juicier, tastier tomatoes than those grown without Optigrow. We need to identify a response variable, specify the response. So in this case, we will evaluate the juiciness and taste of the tomatoes by asking a panel of judges to rate them on a scale of 1 to 5 in juiciness and taste. Then we come up with our different treatments. We want to specify the factor levels and the treatments. In this case, we only have one factor. It's the fertilizer. So we're going to have 3 treatments. 3 plants without any fertilizer, 3 plants with half the amount of the Optigrow, and 3 plants with the full amount of the Optigrow. These treatments are also our levels. When we only have one factor, our treatments and levels are exactly the same thing. Note, I'm also using replication here because I have 3 plants within each group. Then we have to identify the experimental unit. In this case, we're going to buy 9 plants of the same variety. You don't want to buy Roma tomatoes and Big Tom tomatoes because those are going to have different flavors and we can't compare it as well. For the experimental design, we follow the principles. We're going to treat each plant the same and control the sources of known variability. So we're going to water them the same amount at the same time. We're going to keep them in an area where they get the same amount of sunlight. Maybe we'll put them in a greenhouse so that way we can really control everything and there aren't any of the outside variables. We will randomly assign the 9 groups, and we could say that we will do this by numbering the plants 1 through 9. You're going to put 9 numbers in a hat. The first 3 numbers you draw out are the control. The next 3 numbers you draw out will get the half dose, and the last 3 will get the full dose. You can describe it that way if you want. Then we replicate. Again, I already stated this. We have more than one plant within each group. And then we want to make a picture. We want to make a diagram of this. Then we're going to collect the data. So in the end, we're going to pick a tomato from each plant and have the judges judge them by juiciness and taste. We'd want to probably have more than one judge, and we can average the results. Once you have your results, you can compare the data and state what your conclusions found. Maybe you found out that there was no difference between half the fertilizer and the full fertilizer, so you can let your money go a little further. Maybe it didn't work at all. Who knows? But you can at least compare and figure that out. Here is an example of the design. I have 9 tomato plants that I started with. I have 3 different groups with 3 plants each. Each one got a different treatment, and then I would compare the juiciness and taste. And for the record, there should be lines that went to here, but I couldn't figure out how to do that. So let's go ahead and look at what we have learned. We've learned that the best experiments are going to be randomized, double-blind, comparative, and placebo-controlled. We have also learned the value of having a control group and of using blinding and placebo controls. That is it for tonight. I hope you have a great night, and I'll see you tomorrow.